Good morning. It is Monday, and it is 8 o'clock in the morning. So, all right, I want to take a minute and look at the project. I've been grading on those. And as I've said before, my overall objective with those is to challenge you, make you smarter. And but I do that knowing that that's going to be problematic in the sense that if I challenge you, some people are going to have good ideas and naturally like math and maybe have more background in algebra and have more success. Other people less success, and you could spend hours on these things but the goal is to learn from it. And it's not a huge part of your grade in this class. So if you have one that doesn't go super well, it's like, that's okay. That's not the end of the world. As I said, I'll try to give you hints without giving it away. It doesn't do any good if I solve it for you, obviously. But in the end, I certainly want you to grow from it. And so I always want to address them, not just kind of grade them and be done with it. So I want to do that now. Spend a little time just talking about how it could have gone. So let's see, my example, I chose the 2 points. And also probably to teach you some things that maybe you don't know, things that I wish you would know from Math 111, but maybe your teacher didn't show them to you. So for me, my 2 points for my chair, I will sidestep. I said on my sheet, I always encourage you, got to read my directions. I said I wanted to know your 2 points. I wanted to know your calculation distance. Some of you gave me Desmos, didn't tell me those points. I said I wanted your Desmos. Some people didn't send me that. Please read the directions because it's very hard to grade if I don't have the stuff I need to have. So these are my 2 points. And my distance was 16 inches. That's what I was shooting for. And the distance between those two is close to 16 inches. And so, okay, cool. How am I going to get these two points to work? So my graph looks something like that. So this is the point -11, 10. This is the point over here, 3, 2. And so since it has a 0 slope, and please feel free to interrupt here and ask questions because I'm looking down at what I'm doing. Since those are 0 slopes, that means the derivative equation would have to be equal to 0. And so these are hints that I left you with in class before we ended up with the day over. Try to give you time to figure this out yourself. But the fact that x is -11 has a slope of 0 means that x plus 11, and this is a Math 111 concept, like the connection between zeros and factors. In other words, x plus 11, if you throw -11 into it, you get 0. But we also need 3 to work. So that means we also need an x minus 3. So the connection between the roots and the zeros, if you will. And so this must be, well, not our equation, but are actually our derivative equation. And so in my case, if I just chose to multiply it out, that multiplies out to 8x squared plus 8x plus 8x minus 33. And so that equation, well, that'd be its derivative equation. And so what I said on my sheet is that's the derivative equation, but we're actually after the red equation, the cubed equation that would produce this. So again, I left you a little bit in class with the fact that, well, how do you undo the power rule? Like what do you take the derivative of to get x squared? Well, it have to be an x cubed. The derivative of x cubed is x squared. And so now I'm hunting for the actual equation itself. But the problem is if I take the derivative of x cubed, I get 3x squared, not x squared. I want x squared. And so, well, there's no reason we couldn't put a number in front of it. So if I put a 1/3 there, wouldn't that 1/3 cancel with this and it'd be x squared? Like, is it the derivative of 1/3 x cubed really x squared? And how would I get an 8x? Well, I'd have an x squared term. When I take the derivative of x squared, a 2 would come down front. Well, I'd get an 8 if there was a 4 sitting here in my case. So the derivative of 4x squared really is 8x. And then 33, if I had a 33x, the derivative of that would give me 33. And so this is my basic equation. That's the cubed equation. And then it's disappointing. Let's go take a look at this because I want to spend a little time with this. It's disappointing, and you might have been disappointed to see this. You're like, okay, I got this. I'm done. This is not a hard project. If I type 1/3 x cubed, I'm failing.
That would have been sweet if that's all we had to do.
Amen to that. In my case, plus 4x minus 33x. And so you should have been in a sense filled with a sense of like, okay, this is awesome. That's going to go through those 2 points. And so it's like, wait a second, that doesn't look anything like it's supposed to look. But if I go up there, is this right? Oh, was it? I lost my squared. If I go up here and look at these points, it's like, well, that's a cubed equation, all right, but it's like, that's not right. I must have screwed something up. But notice I didn't. Like, that really has a peak at -11. So remember, notice the y coordinate wasn't part of this. So my points were -11, 10. And the point is, well, notice that's like -11, 400 or something, 402 or something like that. But notice the -11 part works. In other words, if you take the derivative of that equation, you really do get a zero slope at x is -11. It's just, it's way too tall. It's way too tall.
Yeah, what I ended up gathering from this experience is that like lots of functions can have the same derivative. You know, like you can, because you can tweak it all these different ways, but it still comes out with the same derivative function out of it. And it was something that I knew throughout the class. I just, hadn't really played with it too much because it was like, okay, well, we got to do this and do this. And,
Yeah. And you're used to, and again, I give you these projects apologetically because it's like you're used to math being teacher tells you what to do and then you go do it and then you're done. But life will just never come at you that way. So I just feel like I'm not doing my job if I don't teach you how to think. Real world is just going to be, as I said, something like design an Adirondack chair, and you'll end up needing math and you don't even necessarily know it when you wade into it. So these are definitely thought exercises. Well, I also left you, excuse me. I also left you with this hint before we even left class. I told you, if you took this expression right here and you multiplied it by something, that does not screw up your slope. Like, that slope still has a 0 at -11, but maybe you understand that multiplying by something changes its steepness. So let's see, what if I make that like 0.2, not 0.2, just 0.2. Notice as I drag that around, it's not screwing up the fact that there is a 0 slope at x is 3 and there is a 0 slope at x is -11. And if you want to visualize it, you can even throw those in there. Throw in x is 3 and throw in x is equal to -11. In other words, no matter, let's change the color of that to black.
You could also put F prime equals 0.
Very true. So the point is, no matter what I multiply my cubed equation that I'm starting to make by, no matter what I multiply it by, it still has a slope at x is negative 11 and x is 3. The slope is still 0. So I can multiply it by something. And notice I could play around with this and get it at least close. Let's see. I'm going to aim for that green dot down there. Notice it's 0.1. And let's see, what if I made it like 0.02, 0.01, 0.001. No, it's too small. Am I going the wrong direction? 0.4. Maybe I should aim for the blue dot just to keep it simple for now. Let's see, 0.2, 0.3, 0.24. Hey, that's pretty close. You see what I mean? Like I'm getting it fairly close to the blue dot, so it's actually hitting it. But notice it's a long ways away from the green one. Well, the other thing I left you with the realization of is the fact that you can also add something to the end of this. I left you with this before class was even over as a hint. I left you with the fact that now you can actually slide, and you should understand that adding something to a graph just moves it up and down. And so notice if I moved it up a little, see how it's a pretty decent split right between those two. Now let's go back and try 0.22, 0.019. I don't know what to try. Let's see, slide this up a little bit. See, I'm getting darn close. Let's try 0.18. Eric, and again, I want to emphasize, like, do you need calculus to build an Adirondack chair? No. Does the Adirondack chair need to be a cubed equation? No. Could be that cubed equation chair would be totally uncomfortable. As I mentioned, it'd be fun to prototype this and see if it actually was. But there are other equations that look like this. And so maybe a cubed equation's totally dumb. But I don't have to do like, isn't that close enough? Like, for the real world, does anybody really care if the distance is not exactly 16 inches? That's pretty darn close. As I said, if all you do is guess on your project, I said this in class, I said it on my sheet. If all you do is kind of guess at it and get it close, the best you can do is a B, which is actually pretty nice considering you did use a little bit of calculus here, because you had to come up with that cubed equation. But how do you actually get those accurate? Notice if I kind of zoom in on it a little bit, it's like, oh, yep, it's missing that point. And I saw people, and I feel some sympathy for this, that like spent, if you will, kind of way too much time guessing at this. So it's like, oh yeah, it looks great, perfect. But this is what I did to grade it. I just went in there and went, oh, I guess it doesn't really hit that point. If I see that, then the best you're going to get 16 out of 20. Because it ultimately kind of misses the point. It misses the point of this question. The point of this question is kind of to learn how to think. And so this is where it kind of gets serious. And so how could you actually guess? How could you actually figure out A and B without having to guess? This is the beauty of algebra. And this is where it kind of became really hard. If you made it to this place, as I hope you did in class, since these are kind of the hints I left you with, the only hints I was really able to give without giving this away were things like, well, you know, how do I make sure it actually goes through those points? Like, what does it even mean for a curve to go through those points? So now I want to take a quick pick of this, and let's go do the algebra. And notice I said algebra, not calculus.
Oh yeah, this algebra was rough.
Yeah, and it's an example of kind of what I'm talking about a lot, because as I said, in my own math experience, I didn't leave algebra speaking the language of algebra very well either. And that's why it's such an issue to me. So I hope you're taking that as like a learning, as kind of an opportunity to learn something, not some kind of a slam on who you are as a person. Like, you don't know algebra. That's not it at all. It's like you're in a spot now that you've taken all the algebra to maybe take some things in a little more deeper way. And I'm hoping what I show you right now is kind of a deeper way of looking at this. So what does it mean to go through that blue point? Actually, let's do the green one first. What does it mean to go through the green point? Somebody put that into words. Like if that red graph is going to go through the green point, what does that mean in algebra language?
I mean, it means that the numbers in the point have to work in the equation that you have.
Exactly. And that's something that you should know. I don't think it's obvious. You're not used to being, as I said, you're not used to being given problems in kind of an open-ended context. And so this stuff hurts. It's painful. But when I show it to you, I think you'll say, in a sense, yeah, I guess I should have known that, or I could have known that. But that's the fundamental issue here is like, what makes that red graph? Well, it's a bunch of points that work in that graph. And so if it's going to go through the point 3, 2, then doesn't that mean 3, 2 has to work in the equation? So take a look at that red equation up there. When y is 2, x has to be 3. Like this is not a super profound revelation. Like does that statement has to be true? Do you agree with that? Close parentheses. And again, stop me because I'm showing you this because I want to teach you something, and everybody's in a bit of a different place. So, okay, well, whatever, big ugly mess. But let's figure out what that is. Like in that parentheses, 1/3 times 3 cubed, that's, I can do that in my head. That's 9 minus or plus 9 times 6 is 36. Minus 33 times 3 is 99. So 9 plus 36 minus 99. I think I got negative 54. So this whole thing, if I didn't screw it up, is negative 54. And so now I have 2 equals negative 54a plus b. This has to be true. Whatever a and b are. Now, I just took some guesses at a and b. And since it's pretty darn close to going through that, if I put in b is 2.8 and a is 0.018, it's going to be pretty close to 2. Now, it's not going to be 2 because, as I said when we zoomed in a minute ago, it wasn't really equal yet. I didn't guess long enough to get it perfect. But here's where I think, it should have, and again, I say that with quotes around it. Here's where you should have went, oh, I see what to do. Simply because don't you have an equation with 2 unknowns? So algebra speak is like, oh, an equation with 2 unknowns. How do I solve that? Well, you don't. There's a million answers that solve that. But what's the important second light bulb here that maybe you see now, maybe you saw it at the time? What else is also true?
You could solve the line for then do a system of equations and rule out, say b equals 2 minus 54a, and then substitute for b.
Yeah, don't we have a second equation here? Like that's not the only point that has to work in this. Isn't there a second point that has to work in it? So, and that's a fundamental concept of algebra. If you have, and you would have spent time in this in different classes, but just not in this way, not in this mode. But if you see an equation with 2 unknowns, you should think I can't solve an equation with 2 unknowns, but I can solve 2 equations with 2 unknowns. I can solve 3 equations with 3 unknowns. So I need a second one. Well, you got a second point this thing's supposed to go through. And what this is saying right now is there's a million cubed equations that go through the green point and have slopes of 0 at negative 11 and 3. But we have a second constraint. It also has to go through the blue point. And so when y is 10, x has to be negative 11. So this is going to be sort of much worse. Plus 4 times x squared minus 33 times x. So again, I'm just punching quickly in my calculator, and I could have already done this, but I'm taking my time a little bit with you so that you get a chance to see kind of process. So I'm taking -11 cubed and dividing it by 3. I'm adding that to 4 times -11 squared plus 33 times 11, since I can see it's a negative times a negative. And unfortunately, I got a fraction, 403 and a third. So I'm just going to cheat and use the math button on my calculator to convert that to a fraction. So that's really regrettable, but I got 1,210 thirds. So it didn't come out a nice whole number like 54.
That's kind of how the problem ended up, though. It's kind of nasty numbers.
Yeah, well, and that's one of the problems with this, and one of the reasons it's important to be able to deal with fractions and decimals and all that, because it's kind of hard to come up with a question that's comes out nice. In a sense, it just means, well, I could have chosen my other 2 points a little nicer. But remember, you don't have to live with that. Like, multiply both sides by 3. I mean, you don't have to have fractions in a problem. But the key here is that you say, well, I need both of these to be true. Isn't that just 2 equations and 2 unknowns? This is not new to you. You should think, oh yeah, totally can solve it from here. As Logan alluded to, you could now solve one of these equations for, say, B, and plug it into the other one. You should have all kinds of methods for solving 2 equations, 2 unknowns. You have a matrix button on your calculator that I'm also going to show you in just a second, where you could cheat to solve this. That's kind of awesome too. Actually, I think I am going to use that method right now, just because I want to show you something even cooler in just a second. But does it make sense? It isn't hard to take this equation up here and say add 54a to both sides. So you have 2 plus 54a equals b. And then if I take that expression right there and plug it in down here, what does that accomplish? What do I have now? Like, why is that cool?
Then you only have one unknown in that equation.
You only have one unknown. Now you just have a bunch of a's. And so now you can solve for a. Now, because of the guessing I already did, I already know a is around 0.018. It's not exactly 0.018, but I know it's around that. And so in a sense, that's a way I can check my work, because my guess got me reasonably close. Actually, now that I plug this in, I think I'm going to finish it that way. Just so I have 1210a all over the top of 3 plus b, which is now 2 plus 54a. So I don't like fractions, so I'm going to multiply both sides. What's that 2 doing there? Why am I? What do I have a plus 2 there? Am I losing my mind? Oh yeah, from the 2 and 54a. So I look at that. Well, before I even do that, I'm going to subtract 2 from both sides. So now this is an 8, and then I don't like fractions, so I'm going to multiply both sides by 3. And I also have to do it to the 54, which is, should be able to do this in your head. 50 times 3 is 150. 12 times 3 is 12. I'm sorry, 4 times 3 is 12. 150 and 12 is 162. It's actually faster than getting your calculator out. And so now I can add those together. And 1210, let's see, what is that? 1372, I think. And so now I'm not saying a is approximately, I'm saying a is equal to. And of course, now because of my check, I want to get my calculator out and see, is 24 divided by 1372 really equal to 0.018? And notice I'm getting a fraction, or I'm getting a decimal, 0.01749271144. I doubt you know this, because you probably haven't studied number theory or something, but you can actually know, because this is a fraction, that this decimal here is going to repeat itself, but I don't see the repeating yet. But it goes ... and goes on forever, which means you're never going to guess it. And obviously that's a really weird fraction. Also, it's kind of a cool trick in your calculator. There's a math button. If you hit second math, you can convert that, or math, you can convert that back to a fraction again. And if it's reducible, then it will reduce it for you, which is kind of nice. So I converted it back, and it says it's 6 over, I know that didn't show much. It says it's 6 over 343. So I didn't have to reduce this. And so I can say A is, I don't want to say approximately, but I can say it's actually 6 over 343 now. And I actually know exactly what that is. And it's going to be perfect. Which means, in a sense, I could go back to Desmos and say, hey, I don't have to guess at this anymore. I can say A is 6 divided by 343. Now, does that make it go through those 2 points? Why isn't it?
You still need to know B.
Yeah, still got to get B right. But notice the distance. You see how it's like a little below the green dot and it's also a little below the blue dot. Notice how it's kind of looks exactly the same distance below both of them, which means if I move this up a little bit, what if I went 2.9, 2.95? So do you see how it's actually, it's really working? Now, again, is it 2.95? I saw this on people's that I graded. You know, when you get closer, is it? No. Darn close, but no. So of course, all I need to do now is just go back in and throw A back into either one of those equations, like that first one, 2 equals negative 54. Actually, maybe throw it into this equation right here. Like this says, there's how you find B. You just take 2 plus 54 times A, which we just figured out is, so B equals 2 plus 54A. And since A is 6 over 343, again, I'm going to cheat on my calculator. Like that looks like a disaster. So I'm going to literally type what that says. 2 plus 54 times 6 divided by 343. It's going to give me some horrific decimal, 2.944. Notice that agrees with the guess a minute ago, 2.95. And now I'm going to say, go to math and say, convert that to a fraction for me. And it says 1010 over 343.
So that was so much easier than what I did.
And that's why I'm showing you this, because like, you know, you're not an expert at algebra yet. So you should have wasted all kinds of time, which actually isn't wasted because you're growing in your strength by trying stuff. And then when I show it to you, you should, what I tell you should sink in a lot more deeply, because it's like, oh yeah, you know, in a sense also you should be thinking, these are algebra concepts I know, I should know, whatever. And so again, I find myself wanting to kind of go back over here and verify all that. Is that really true? Is B 1010 divided by 343? This is what I did to grade your project. I just kept zooming in on it a ways and said, no matter how much I zoom in, does it just seem to be perfect? And the answer, if it suddenly separates, and it's like, wow. If I had to zoom in like I just did and it suddenly separated, I realized, oh, what a bummer. This person spent hours like trying to get it perfect, which is kind of cool. But it's like you work so hard because you don't speak the language of algebra. And the idea behind algebra is you don't have to guess at stuff. That's what's really cool about algebra or about math in general. Like, I wonder what'll hold this bridge up. Well, let's build it and then we'll drive a car across it and oh, that person died, the car broke. Okay, well, let's build it a little bit bigger. I mean, that's what you did if you were guessing. But it turns out in the land of math, you can actually calculate how much the bridge will bend under weight and so forth. And you don't have to guess. And then you can build the bridge and just know it's going to work. And so that's the beauty of speaking the language of math. And so that's really perfect. Now, again, if you think of this as like you're building an Adirondack chair, it's like, that's really stupid to be perfect. I mean, why would it need to be? But that's not the point of the project. The point of the project is to learn how to speak and think about how math works. Let me show you a second way though. Actually, I want to show you one other thing first. Let's see, how do I unshare? Do you know this? Did your Math 111 teacher show you the glories of the Matrix? Top 5 best movies ever, Matrix? If not, you need to know it. And so you're getting it now. So right here, and please interrupt if you've never seen this before. And if you haven't, it's not your fault. It's, well, our fault, my fault. Right above X1, it says matrix, second matrix. First, turn on calculator. Second matrix. and I can math, name it, or edit it. I want to edit it. And what I just had a second ago was what mathematicians call a 2x3 matrix. I sort of wish I had written this down before I came over here, but I guess I'll just ask you to remember me. Those two boxes, those two equations that I remember, how the first one was 2 equals negative 54ab, 2 equals negative 54a plus b. Because of that, that's an equation that's got three numbers, a 2, a negative 54, and a 1. And then the second equation also had three numbers. And so it's 2 rows and 3 columns. Well, the beauty of a matrix is you go in here and say, I would like to edit this first matrix. And what size do you want it? I want it to be a 2x3 matrix. And notice your calculator sets you up then to enter in, notice 1, 2, 3 numbers, drop down a row, 1, 2, 3 numbers.
You're doing.
Say again?
Yeah,
What's wrong?
you're not screen sharing.
I'm not screen sharing. What we have here is a failure to communicate. That is user error. So right here, I'm going to do this again really quick. Second matrix, you can name one, do math, or edit it. I'm going to go over to edit. You say edit, and then it says, what size matrix would you like? And I typed 2, 3. And then when I typed 2, I'll do it again, 2, enter, 3, enter, it sets me up with 2x3. In other words, 6 numbers that I can type in. And watch carefully what I typed. That first equation was 2 equals, so I typed 2, and then equals negative 54, so I say enter, and then negative 54a, and then plus b. Well, that's plus 1b. So there I entered the numbers of the matrix. Unfortunately, though, this is a great mnemonic device, but you've got to put it in correctly. Does anybody know that I put that in incorrectly? Just curious. How do you have to enter numbers into a matrix? Unfortunately, the equal sign's got to be on the right side. So that means I have to think of that equation. Instead of 2 equals negative 54a plus b, I have to think of it as negative 54a plus b equals 2. So the negative 54 has got to go here. So negative 54a plus b, well, that's plus 1b equals 2. There, now it's in there correctly. And then the second equation was 12 10 thirds a. So 12 10 divided by 3, that's 12 10 thirds a. Again, plus b, so that's plus 1b equals 10. So now I've entered the numbers in the matrix. So the equal sign has to be on the right. You also got to be careful to keep them lined up. In other words, this is the A column, this is the B column, and this is the equals column. You can't mix them up. So this is a really cool mnemonic device, or a kind of an amazing shortcut. So now I say, awesome, I'm editing the matrix. Well, I want to quit that. Second quit. I'm out of here. Back to a calculator. Now I go back to matrix, except for this time, instead of editing it, I want to go over to math. Notice there's a whole bunch of stuff you can do to a matrix, which of course makes no sense. Determinant, transpose, dimension, blah, 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 blah. Bunch of crazy stuff. This right here though, and again, what I'm showing you is the cheat buttons, if you will, kind of like when I showed you dy dx on your graphing calculator early in this class. Reduced row echelon form is what that stands for. And actually, I'll elaborate on that a second. So it's basically saying, what do you want to do reduced row echelon form on? Second matrix, I want it to be on, well, matrix A. So I say enter. What is that saying? First of all, do you recognize those numbers? What is that first equation saying? It's saying, well, wasn't the first column 1? So that's 1a plus no b equals 0.017. Hey, that's saying a equals 0.017. The second one is saying no a's plus 1b equals 2.94. Hey, that's saying b equals 2.94. That's exactly right. And if I go to math, as I mentioned earlier, and said convert all that stuff to a fraction, then I'm getting the exact answer to that. Like what I showed you here is effectively a whole subject in math called linear algebra. There's a 261 math class after you take calculus that goes into this. So you learn like, what is a row echelon form and why does this work? And, you know, where did all this come from? And, you know, I'm just showing you how to push buttons right now. But that's a cool way to solve systems of equations. We're going to use that again in just a second. So I'll get a chance to show you that one more time because I want to show you just another thing that you could have thought if you spoke the language of algebra. Here's a totally different approach. I'm going all the way back to the start of the problem and saying, find the equation. Would you agree that the f of x equation, since the derivative had two answers, that the original equation must be something cubed plus something squared plus something x plus something? Would you agree that's the way the equation would have to look? Which of course is like, well, that's not helpful. Would you further agree that we don't want just any cubed equation? We also want the slope to be 0 at a certain couple of points. Well, can't you take the derivative of that equation? Now remember, a, b, c, and d are just constants and we don't know what they are yet. So isn't its derivative, if I bring the 3 down front, 3 times a x cubed, and again, a is a constant. If a is not a constant, then we have to think, oh, product rule. A is just a number. We just don't know what it is yet. That's why I'm not doing product rule. And we took the derivative, so that's squared, right? Isn't that the derivative? What's the derivative of bx squared? Well, don't I bring the 2 down front to multiply by b, and then the x goes down by a power? Isn't that the derivative equation? Now, that again, that looks like, well, great, good for you. You wrote down what you're after, but it's like, how's that supposed to help anything? Well, don't you know a bunch of cool stuff here? Let's just think about what you know. Don't you know that f of 3 has to be 2? Was 3, when x is 3, y had to be 2? Wasn't that one of my points? So couldn't I plug this into that equation? So, and didn't I do this a minute ago? So let's see, 3 cubed, I'm plugging in x is 3, so 3 goes there and there and there. 3 cubed is 27, so that's 27 times a. 3 squared is 9, so that's 9 times b. 3 times c is 3 times c. Again, you should look at that and think, good for you. Like, what good is this doing? Nothing. This is a total waste of time. Don't we also know that when x was negative 11, y was supposed to be 10? That was my second point. And so if I put, what am I doing? Get all excited, can't function. When x is negative 11, y's got to be 10. So that means if I put 10 in for y, x has to be negative 11. Negative 11 cubed is some big number, 1331. So it's negative 1331. That's 11 cubed, again, times a. And then 11 squared is 121. So that's 121 times b. And then 11 is x, so 11 times c plus d. Where am I going with this? Like, why is this? Why is that going somewhere? Well, again, this is the logic. This is the logic of algebra. Notice I have 4 unknowns. Can you solve an equation with 4 unknowns? Yes. If you have 4 equations, you can solve an equation with 4 unknowns. Well, there's 2 of them. Here's the next 2. Don't I also know, now that I can realize how much room I need, I'm going to move this up. Don't I also know that when x is 3, what's the slope supposed to be for me?
0.
0. So doesn't that imply that 0 equals 3 times a times x, x is 3. So I have 3 times 3 times 3, I have 27a again. It's kind of a coincidence that's 27 again. And then I have X is 3, 3 times 2 is 6, so that's 6B, and then there's just C is just C. Isn't that a third equation? Now it doesn't have a D in it, but isn't that a third equation that has these unknowns in it? And finally, don't I also know that at negative 11, the slope at negative 11 is also supposed to be 0. So 0 equals, again, I'm putting in negative 11 for X here. Negative 11 squared is 121 times 3 is 363, I think. So that's 363. And then again, the A comes along for the ride. And then I have negative 11 times 2, which is negative 22. And then I have C. Hey, look, 4 equations, 4 unknowns. Well, that'd be terrible to solve by yourself by hand, but not terrible if I go put that in the matrix. So just so that you understand what I'm sticking in the matrix, this is going to be my A column, my B column, my C column, my D column, and then kind of my equal sign. There's some number over there. So for that first equation, I have 27A, 9B, 3C, and then a D, which is 1D. There's a 1 in front of it, and that equals 2. Notice that, again, the equal sign's got to be on the right. My second equation, I've got 1331 for A, 121 for B, negative 11 for C, 1 for D, and that's all supposed to equal 10. And then for this equation, I've got 27 for A, 6 for B, 1 for C. What do I do for D?
0.
0D. Isn't there 0 Ds? And then it's all equal to 0. So what's on the other side is an equal to 0. And then the last one's the same, 363 minus 22B plus C, no zeros, and it's equal to 0. There's my, what size is that matrix in the language of linear algebra? Somebody
4
tell
by
me.
5.
Yeah, 4 rows, 5 columns. So it's considered to be a 4 by 5 matrix. So second matrix. Forget to turn on calculator yet again. Second matrix. Go over to edit. I could type over the top of the 2 by 3, but I'll go down to matrix B this time. Notice it's saying, what do you want, a 1 by 1 matrix? No, I want a 4 enter by 5 matrix. And notice it's so big you can't even see all the numbers. See how there's a couple lines over here on the side? There's like more numbers to the right. So now I'm just going to start typing all this stuff in. I had 27A, 9312. So 27, enter 9, enter 3, enter 1, enter 2. Notice how you can see the bracket now because you're over here. If you hit enter, it goes back to the start again. So I'm just hitting enter every single time. Negative 1, 331, enter, and then it was 121. Negative 11, 1, and 10. And then it was 27, 6. I wrote C, but 27, 6, 1, 0, 0. 27, enter 6, enter 1, enter 0, enter 0. And then it was 363, negative 22, 1, 0, 0. So I have all 4 by 5. I have all 20 numbers in the matrix. Maybe I typed one of them in wrong. If you saw that, please tell me because I didn't. I just was looking down. So now I say second quit. Go back to matrix, except for this time I want to do math to my matrix. Reduced row echelon form, please, of what matrix? Well, in my case, B. I want that matrix. And it says, there you go, done. Notice this first row is now 1A plus no B plus no C plus no D equals 0.0 0.058. Yeah, that's cool. That means A is 0.00158. Again, I can just to reference it, I can go back and change these to fractions. And let's see, I don't even know, how do I get over there to see them all? Oh, I guess I just hit arrows. So how come that first one isn't 6/343? I thought that was the number.
Is it because it's not factored out?
Yeah, what this is multiplied in. Remember that x cubed term had a 1/3 in front of it? So there was 6/343 times a third. And so this is actually distributed into the whole thing. And so this is literally telling me that original problem was y equals ax cubed plus bx squared plus cx plus d. And this is telling me what those numbers are. And now I could type this into Desmos, which I'm not going to take the time to do. And I'd get that exact same kind of red graph that I just got a minute ago. And so again, this is what mathematicians do is they come up with interesting questions. Sometimes it's, practical, like I'd like to build a house. Other times they're just curious, like how is there a way? And this is where this problem came from for me, because as a teacher in this section that I'm teaching you right now, I try to come up with problems where, if I say find the slope or find the maximums and minimums of this curve from 4.1, and I'd like it to come out a nice, neat whole number for you, I realize, my goodness, those are hard to come up with. It's really hard to come up with one that hits a couple of points and makes a nice problem. And that's where it came up from me. That's where this problem came from ultimately. The Adirondack chair was just kind of a fun addition to the problem to make it maybe a little bit on the practical side, if you will. But that's what mathematicians do. They just ask questions that they think are interesting, whether it's just playful and, stretching your mind, or whether it's like, let's build a bridge and not have it break and make some money. But that's where this came from. And you can see why, what I just showed you in the calculator is pretty like, wow, what is all that stuff? Like there's a class there. There's a class of stuff to consider. There's a lot to know. All right. How's your brain? Is it mush?
I'm just glad we didn't have to do row echelon form by hand. I remember that.
Yeah, your math teacher should have showed you this. I mean, this is something you should have done near the end of Math 111.
Yeah,
Again,
I don't remember that.
did it.
111.
I did it once, and I understand it well enough to apply it when it comes up in the world. Are two very different things. And that's kind of what I mean about the difficulty ultimately of speaking the language of algebra.
I do know when I took Math 111, it was the first math course we had to take over Zoom.
Yeah, that helps a lot.
Oh, it was sweet.
Any other thoughts or comments on that? Does it at least tie it together? Again, I don't think it personally is the end of the world. Like if you just kind of guessed and got a reasonable answer, that's why I gave you a B. You missed a whole bunch of the cool things you could have known, but it also could, take you hours and hours and hours. But my hope is that whatever, what I just showed you is like, oh, wow, yeah, that's totally cool. I get it now. Or, I learned something. Isn't that the goal? Like you learned something. Good. We should be high-fiving then. And
So like I did it like a completely different way than any one of those ways.
what'd you do?
Well, to get A, I took the y from 0.1 minus the y from 0.2 over like
That's not different.
f of 4, but plugging it into that equation that the derivative or the antiderivative equation, well, not antiderivative, but the equation we came up with, put in the middle, and then putting it f of 4 minus f of 19, which are my 2 points.
That's not different. You did exactly what I did right here.
Oh,
It's not different.
okay. Yeah, I guess that makes sense.
Where I made the mistake was I didn't realize that Desmos stopped counting decimals after 3 places. So I just thought, oh wow, it's exactly point whatever away from that. So I'll just take that.
Oh,
to
yeah.
correct my point.
If you didn't get, if you rounded what you typed into Desmos, then my assumption was you guessed your way to it, and did not kind of do this process. But if you didn't type the fraction into Desmos, then it's not going to hit, because the fraction, the decimal goes forever. So I don't care if you carry it out 9 decimal places like I just did a minute ago, it's still not going to be perfect. So you have to put the fractional answer in there. If you did the math on the fractional answer, tell me that, because I understand that if you just typed in the decimal version of it, even though you knew it wasn't perfect, I assumed you just guessed your way to the answer, and maybe that's not true. So
I did the math.
yeah,
All of the math.
yeah, send that to me. There were a couple people who had the number in front of the parenthesis. For me, that was 6/343. They had that accurate, and then they had a decimal at the other end of it, and I was like, what? That actually makes sense, because that was one of, I think that was you, Faith. Okay. I think that was worth our time. I have something really short and actually really simple, and maybe a little bit odd to show you now. And it kind of pertains to all of this. But again, what we're really looking at in chapter 4 is what do derivatives tell you about a function? And the main thing we said on 4.1 was derivatives tell you when the slope is 0. I mean, that's a way to find the maximum or a minimum of a curve, because that's just a particularly interesting point. Of course, a derivative tells you any slope, but a 0 slope tells you a very interesting particular location on a function. And so let's consider something else. The mean value theorem, mathematicians call it. And it's almost embarrassingly simple. And I would encourage you to, I don't have time to do this now because we spent too much time on the project, but I'd encourage you to look up what the book says about this. I might read it to you in a minute if we have time, but it's just such a simple idea. And it's almost humorous. Let's consider this function for a second. If I say, I don't know, negative x, I want a parabola that's upside down. Would you agree that's an upside down parabola? And then after that, I don't really know. I'm just going to throw in some stuff. I don't know, that. So there's that function. And let's go take a quick look at it just so we don't have a terrible looking graph rather than just make an awful graph. I think I'll just say y equals negative x squared plus 4x. Was it minus 2? If it wasn't minus 2, I'll change it to minus 2. Now let's take it up in the air a little bit now that I'm looking at it. Let's make it like plus 5. There we go. And let's see, I want to find some points that it goes through. Like, looks like it goes through the point 8, 1. I'm just cheating to get this. So I just wanted to find some exact answers to it. So I'm using my algebra skills. 8, 1. No, 1, 8. Man, what a lame-o. 1, 8. And then it also looks like it goes through the point 4, 5. Did I actually get it in the right order this time? Yes, I did. So it goes through the point 4, 5. So, okay, cool. Let's label that 2. So what I'd like you to do quickly is, well, find the average. What we talked about before we knew calculus was the average rate of change. Like, what's the slope between those 2 points? Maybe we'll get lucky and it'll come out nice. Maybe it won't. But what's the slope between those 2 points? 1, 8, 4, 5. You find the slope of that. Should be able to almost do that in your head.
The negative 1.
That looks right, because you're ultimately taking 8 minus 5. I don't like negative numbers, so I'm going 8 minus 5, which means then I also have to go 1 minus 4. And so I got 3 on top, but negative 3 on the bottom. So I got a slope of -1. That's the average rate of change. Again, this is kind of like saying, well, at year 1, if your company was worth $8 million, and then at year 5, it was worth $5 million, what's the average rate of change? Does it make sense? What you're finding out is, well, what was the trend during that time period? I'll just let that be approximate. So that is the slope of that line. And does the concept of average rate of change make sense, and why it doesn't totally tell the story? Basically, it means you were dropping $1 million a year. Doesn't that make sense in this context? Now, is that actually what happened? No, it actually went up for a while and actually kept getting better and better until it hit this peak. And of course, we know that's a really interesting point. And then it actually dropped way faster. And so along the average rate of change, or the average slope between those, and I'll even kind of throw the word average in there, the average slope is -1, but we had slopes in here that were still positive. There's a positive slope. There's a 0 slope. Here's a really steep negative slope, like -4 or something. You had slopes all over the place, but the average slope was -1. What the mean value theorem says is there must also be some place of all the slopes that existed, there must be some place here where the slope, and I'd say it's about right there, wouldn't you? Again, I'm showing this to you in English because it's so simple. Would you agree there's some place on there that has the exact same slope? There was some point in time, even though, as I said, the country or the company was going up in value and still had a positive slope. Here, the company's growing. It's growing, still growing good. Now it's not growing as fast. It's leveling off. It's not growing as fast. It's not growing at all. The slope is 0. But there must be some place between those two where the slope is identical to the average slope. Could you find that place? Where is that? You should be able to find that right now. I don't need to teach you anything new. I just want to give you a second to think about it. Same
Wouldn't
slope.
you just set the derivative equal to -1?
Exactly. We know the slope is -1 now. We know the average rate of change is -1. And so can't you just set the slope equal to -1 and figure out where that point actually is? Notice you can kind of tell based on my drawing, it actually looks like it's at 4. I can't see the bottom anymore. 1, 2, 3, 4. I can't tell what those boxes are worth now. The mean value theorem basically says that that point has to exist. So since f prime, I'm catch up to you a little bit here. Since f prime of x is actually equal to -2x plus 4, notice the derivative taking is not the hard part. That's just a power rule problem. That's the derivative. That's the equation that tells me the slope anywhere. And so there must be some place where that slope is equal to -1. Well, that's easy to solve. Notice it's not 2 equations, 2 unknowns, or 3 equations, 3 unknowns. It's 1 equation with 1 unknown. Okay, good. I can solve that. If I subtract 4 over to the other side, I get -5. If I divide by -2, I get 5/2 or 2.5 or 2.5. And so that's what I'm saying this point is at, is that x is 2.5. Again, that looks reasonable. It's between 1 and 4. In this case, we got kind of lucky that it's exactly halfway between 1 and 4. That isn't always the case. So I found it.
Yeah, I was actually going to ask you if it was going to be halfway between the 2 points.
It is, because this is such a nice graph. But does it make sense that if I was at the point 1, 8, and then also at the point 4, 5, basically the theorem goes on to say this curve could be anything. Like it could actually be doing this. As long as it's smooth and connected, as long as nothing weird is going on, there's no holes in the graph. And the calculus way of saying that is it's continuous. It's a continuous graph. There's no holes in it. And it also says it's continuously differentiable, meaning there's no spikes in it. You may remember that discussion. Like if a graph has a spike, you can't tell what the derivative is there. So they'll say it's continuous and differentiable, which is sort of code for it's just a normal smooth curve. There's going to be some place on that where the slope is -1, but it isn't necessarily in the middle. And notice in this case, in the formula, the theorem will go on to say there's at least one place. Would you agree there's one there and one there? And actually one over here too? Like there's 3 places there where the slope is -1. So it doesn't just have to be one. Your book assignment is not going to give you something that looks like this. There's just going to be one answer.
Well, that just means that in that case, you probably have like a cubed or whatever equation or more. And when you actually did the math, you would end up with multiple answers.
That's right. So just to kind of highlight the way the formula would be in the book, it's going to say something like this. A second ago, to get this slope, didn't we do this? We went 8 minus 5. Well, what was 8? Wasn't it actually the function? I mean, in order to even get 8 in the first place, didn't we have to put 1 into the equation? So in a sense, it's the y coordinate. I don't know which order to put this in, but the y coordinate of 1 minus the y coordinate of the other. Isn't that what we just did a second ago? That's how we got. I cheated off the graph, but in order to figure out if I stuck in, and let me go back and just write this because this is the way your book will look. It'll say, I'm interested in this graph on the interval from 1 to 4. Remember, that means those are x's. So they're saying, hey, I'm only, this graph goes forever in every direction. I'm only interested in between x is 1 and x is 4. So use the mean value theorem to find what the average rate of change is, or the mean slope, or some word that's a synonym for that. So I found the y coordinate that went with that by going, well, I guess I got to figure out what f of 1 is. So I put 1 into that equation and I got 8 out, and I put 4 into that equation and I got 5 out. I just cheated to get those points off the graph. And so didn't we go 8 minus 5? Well, isn't that f of 4 minus f of 1? And then on the bottom of that, we went, well, the 2 x's subtracted. X is 1 and x is 4. We went 1 minus 4. So isn't this b minus a? Like, isn't that how we got the -1 just a minute ago? So whatever that slope is, does it make sense? This is the average slope. Average slope between the x's, in this case, a and b. Those x values, that's the average slope between those. So I just went y minus y over x minus x. That's not hard. I got the average slope. But the curve itself is curving and going crazy. And so there must be, the mean value theorem says, some place on the curve, some location that gives you the same answer. And so this is what the book will say. This is effectively what the mean value theorem says. It looks complicated, super simple. And so what we just figured out a second ago is, yeah, there must be some place, some location. Notice C has to be between B and A. So if I said A is less than C is less than B, in other words, C is between those two. C is somewhere, it must be some number in between there where we actually end up with the same exact slopes, the same exact average slope. So connect that to what we just did. Let's try this again with just another equation. Let's try this without even looking at a graph this time. What if it was like, I don't know, f of x equals 2 square root of x plus 3 or something like that, some square root graph. And I say, I am interested in the interval between, let's see, I want to be able to take the square root of it. So let's go 1 to 4. I can take the square root of 1 and the square root of 4. And so I'm interested in that interval. And so we can find the average rate of change. And maybe you remember that, this graph looks something like this. I don't know, it's like a downward curve. And so we're looking at a couple of points kind of like that, something like that. So, what's the average rate of change? Well, first I got to figure out, like, what are my y coordinates? When I put 1 in, what do I get out? Square root of 1 is 1, times 2 is 2, plus 3 is 5. So f of 1 is 5. When I stick 4 in there, the square root of 4 is 2. 2 times 2 is 4, plus 3 is 7. So I get a 7 out. So there's my points. And so now I have these coordinates. So I have the point 1, 5. Then I have the 0.47, and so now it's easy to find the average slope, the average rate of change. And so I can say easy, 7 minus 5 over 4 minus 1. So I got a slope of 2/3. Great, that's the average slope. So mean value theorem says there must be some place in there where the slope is that average slope. From my rough picture, this is the slope we just calculated. The point we're after is not here because that slope is too steep. It's not here, the slope is too flat. Does it make sense? It must be in the middle of that somewhere. That's kind of the logic here. So it must be like here-ish somewhere. So the question is just, where is that? Where's that C point down there? Where am I? It's definitely between 1 and 4. Where is it? That's not hard. I just say, well, let's take the derivative and set it equal to the slope of 2/3. This is my average slope. So let's go take the derivative of our expression. What's the derivative of, let's see, what rule is this? How do I take the derivative of square root of x? Let's see, square root of x is actually x to the 1/2 power. So the 1/2 comes down front, multiplied by the 2, that's a 1, that's nice. And then I take x and subtract 1/2 and subtract, and then the derivative of 3 is nothing. So there's the derivative. Maybe it's nicer to write it like this. Do you agree that it is nicer to write it like that? Maybe it isn't, I don't know. Again, hopefully this section is not like, oh, how do I take a derivative? Hopefully chapter 3 is with you, but it's like you do have to bring that stuff back. So then, is there some x where 1 over the square root of x is equal to 2/3? As I told you, I don't like fractions. I see fractions and equal signs, I get really happy. I don't like fractions. Multiply both sides by 3, multiply both sides by the square root of x. There, I got no fractions. And so x, square root of x would be equal to 3/2. And so x would be equal to square both sides, 9/4. So notice that's 2 1/4. And to my question before, notice that's not in the middle. It's not halfway between 1 and 4. This is the same x as we had a minute ago, 1 and 4. Halfway between that was 2.5. This is a very different graph. It's not halfway between it. But at 9/4, I would actually get that exact same slope. That's kind of cool. That's what the mean value theorem says. In a sense, it's kind of a theoretical thing. It's like it's a proof that things exist. I mean, and we're going to be using this for some of the things we do later on in this class, but it kind of has to do with, if I have this curve that's continuous that looks like this, and I plug in some x value over here and I get a positive slope, and I plug an x value over here in and I get a negative slope. Does it make sense if they're smoothly connected that there must be some place in the middle that's a maximum, a zero slope? That's kind of the logic as to what this is doing for us. It's just telling us that things exist. on smooth curves. So you can go find them. It's not hard. It's not hard at all. You try this one really quick. So that was a radical function. What about a fraction? Like, I don't know, 2 over x minus 3. And let's put this on the interval of 7 to 13. I'm not writing out all the details, but between 7 and 13, what's the average slope? And can you find the point on the graph that has the exact same slope? Again, that's the interval of x's. I'm going to make a graph of it while I give you a second to think about it. Always helps to have a graph. So take a look at my graph to verify whether your answer makes any sense. You should see now that, oh, that average slope is a small negative number. I better have got a small negative number for the slope or I did this wrong. I'm gonna catch up to you so we don't run out of time. So I plug 7 into this and apparently get out a half. So that means the 0.71 is one of my points. I plug 13 in and I apparently get out 0.2, which is 1/5. So there's my 2 points. So my average rate of change or my average slope, slope's changing all the time on curved equations, but the average between those two is y minus y over x minus x. A little bit of logic. As I told you, I don't like fractions. What could I do to get rid of fractions? I'm going to multiply the top and the bottom by 10. So this becomes 5 minus 2 over 70 minus 130, which is 3 over negative 60, which is negative 1 20th. I bet you that was easier than what you just did. I bet you added fractions together. Should be able to do that. Let's see, double check. Did I screw anything up? 5, 2, 70, 130, negative 63. I don't think I did. Looks reasonable in the picture. Small negative number. Cool. So the question is, can I find a place on the curve that has exactly the same slope? Well, I got to take its derivative. Derivative. Well, I'm going to just do the classic quotient rule. Classic quotient rule says derivative of the top times the bottom left alone minus the top left alone times the derivative of the bottom, all divided by the bottom squared. So 0 makes that go away, so I end up with -2. So I get -2 over x minus 3 squared. What else could I have done? I'm not going to write this down, but I could have changed it to 2 times the expression x minus 3 to the -1 power. I could have moved it to the top and made it -1 power. That would have been good. Then I could have just done the power rule and the chain rule. That would have worked too. There's my derivative. And so what I'm interested in is there some place where, is there some x, find x such that -2 over x minus 3 squared is actually equal to the slope that I'm interested in finding. I don't like fractions, multiply both sides. So I get -2 times 20 is -40. X minus 3 squared times -1 is -x minus 3 squared. I get rid of the negatives and I have x minus 3 squared equals 40. I square root both sides. I have x minus 3 equals the square root of 40. I add 3 to both sides. I get 3 plus the square root of 40. Technically, it'd be 3 plus or minus the square root of 40, because there's actually 2 places on this graph where the slope would be -1/20th. But in my case, I was interested in the one that fell between. What was the range I was working on? I was working on the range between 7 and 13. So hopefully that number is somewhere between 7 and 13. I want to figure it out real quick. 3 plus the square root of 40. Okay, good. That's approximately 9.32. Of course, what would be cool is to go back into Desmos then and just cheat and say, check this out and say, is f prime of whatever that number was. Actually, I'll type the whole thing. 3 plus the square root of 40. Hey, look at that. It says it's -0.05. That's -1/20th. So apparently I got this right. That's kind of cool. Checked. Again, it'd be even cooler to maybe draw a line between those 2 points and then find the equation of the line as well. This is not hard. It's just interesting. Found it. The mean value theorem guaranteed there'd be a place where this was true, and we were able to find it. It's just good practice for your calculus skills, really. I got to say one more thing, but I wish I could just say, have a good day, but. Rolle's theorem is the same exact thing. There's nothing new about it. It's just that Rolle's theorem says that these 2 points, the 2 points we're interested in, aren't at different heights. Rolle's theorem says they're the exact same height. If they're the exact same height, same y value, then what does that mean the average slope's going to be? What's
0.
the slope of that going to be? Yeah, the slope is going to be 0. So that happens only when f of b equals f of a. In other words, they have the same y value. If that's the case, the slope is 0. And that's kind of what we're using, what we've been talking about lately, in the sense that, well, you know, if the slope between those 2 points is 0, then there must be, it's no different. This is mean value theorem. It's just that rolls is named separately because in this particular case, 0 is a particularly cool location, excuse me. So, you know, there must be some place in between there where this peaks out.
How
There must
did
be
you
some
get
place where it's
x
also
minus
0.
3 squared equals 40?
Say again?
How did you get x minus 3 squared equals 40?
Thank you. Because I said I don't like fractions back here, so I multiplied the 20 by both sides to get rid of it. Got negative 40 on that side, and then I multiplied x minus 3 squared up to that 1 so that I had this statement. And then I saw, hey, look, they're both negative, so I'll multiply both sides by negative 1. And then I square rooted both sides. I square rooted the x minus 3 to get rid of the squared, and I square rooted the 40, and then I added 3.
Oh, okay. I put negative 1 over 2 and or 20 in for the x.
Yeah, there's more than one way to do it. I'm just pointing out that there's a lot of easier ways to do algebra, and generally speaking, getting rid of fractions makes less algebra mistakes.
Okay.
So your assignment will say things like, you know, can you use Rolle's theorem for this problem? And if this had been a Rolle's theorem problem, then these two numbers would have came out identical. Does that make sense? They have the same exact y coordinate, have been like 1/2 and 1/2. Can you use Rolle's theorem for this? The answer here is no. Look, different y values. You can use the mean value theorem, and then you got to find the slope yourself. The cool thing about Rolle's theorem is, hey, look, these are exactly the same. The two y values are the same. Okay, well, cool. That means I know the slope is 0. It's the average value of the slope is going to be 0. And then I just have to go find a point where this, I'm just setting the slope equal to 0 instead of equal to negative 1/20 or whatever the case may be. Again, this is Monday. If you're smart and you have time, you would go wade into that assignment. There's only 6 questions. This isn't a super important concept. And if you have any trouble, then tomorrow you say, hey, I got stuck on question 6. And I'd almost prefer you ask me before class tomorrow, just because there's probably, you're not probably the only one that would have that question. But you know, as long as you learn, if you can speak the language, you're going to read the assignment and go, what? You know, because they're using words like continuously differentiable function and so forth. But this is an easy concept that looks complicated when you speak it in calculus language. But I hope my examples will make it clear. All right, get yourself out of here. Say after if you want me to elaborate on any of the things that I said, including the project. Otherwise, I'll see you tomorrow.
Okay. Doug, I'm not going to be in class tomorrow.
Yes.
Just wanted to let you know.
I know you're going to scavenger hunt.
Yes.
I love it. Where is it? How's that working? Is it online?
Yeah, it's over Zoom this year.
That's cool. What school are you connected to? I forgot.
Logos.
Logos. All right. Good luck. Yeah, I'm glad you're going. That's a great experience. We'll catch up.
Okay, thank you. Bye.
Yeah, see you on Wednesday.
Hey, Doug, did you get that? I resent that email this morning.
I saw it, but didn't have time to look at it yet.
Okay, awesome. I just want to make sure you got it. I thought it was actually due this morning. I didn't realize it was due Sunday, so that was my bad.
No worries.
So I apologize for that. All right, have a good